What is energy? Energy is waves. To understand this, we'll examine three fundamental principles in quantum physics: wave-particle duality, superposition, and the observer effect. To gain a deeper understanding, let's journey back in time and explore the historical experiments and discoveries that gave rise to these fundamental principles. In 1804, the English scientist Thomas Young conducted the first double-slit experiment where photons passed through two slits onto a wall, resulting in interference patterns, indicating that photons had wave-like properties, which was supported by Christian Huygens' wave theory of light. This astonishing discovery challenged Isaac Newton's particle theory of light, which had suggested that photons were particles. However, the wave theory of light faced controversy in the late 19th and early 20th century due to the discovery of the photoelectric effect, which illustrated a photon's particle-like properties. This begged the question, were photons particle-like as initially thought, or were they wave-like? In 1924, more than a century after Young's experiment, French physicist Louis de Broglie proposed the de Broglie hypothesis, asserting that matter exhibited both particle-like and wave-like properties. Meanwhile, through 1923 to 1927, American physicists Clinton Davisson and Lester Germer were studying the surface of nickel. They conducted experiments involving shooting electrons at a crystalline nickel target to understand how electrons interacted with the surface. Unexpectedly, they observed a diffraction pattern, echoing the findings of Young's experiment. This breakthrough solidified the Broglie hypothesis, laying the foundation for what would later be known as wave-particle duality. By the 1930s, the groundwork for modern quantum theory was laid, emphasizing the role of measurement or observation, which was understood to determine a particle state. By the 1950s, the Copenhagen interpretation gained popularity as a model for interpreting quantum mechanics, involving wave-particle duality and measurement as core principles. This interpretation was widely accepted due to its practical approach. Throughout the 20th century, scientists expanded the double-slit experiment to explore other subatomic particles. In 1961, German physicist Klaus Johnson conducted the first version of the experiment with electrons, which yet again yielded interference patterns, confirming wave-particle duality. As the wave-like property of a particle became evident, it demonstrated that a particle can exist in multiple states simultaneously, a concept which became known as superposition. In 1965, American physicist Richard Feynman proposed a thought experiment for the double-slit experiment. He suggested adding a detector in front of the slits, believing this would cause the interference pattern to disappear. This thought experiment was later confirmed in the 1980s and 90s when witch-path experiments were conducted. These experiments involved detectors that measure which slit the particle passed through, leading to the collapse of the particle's superimposed state, restoring its particle-like properties. This breakthrough demonstrated that particles behave like waves when unobserved, but like particles when observed, a phenomenon which became known as the observer effect. Now that we've explored the historical evolution of quantum physics, let's take a look at what we've learned. In the realm of scientific discovery, early debates between particle theory and wave theory spurred exploration into the fundamental nature of reality. Along this journey, three pivotal principles of quantum mechanics were unearthed: wave-particle duality, superposition, and the observer effect. These principles bridge the gap in our understanding of particles and waves, offering a unique insight into the fundamental nature of reality, and revealing that both particle theory and wave theory held partial truths about the universe. Let's reflect on the profound implications of these insights. Quantum physics proves that everything is fundamentally comprised of waves. These waves are the energy that flows throughout the universe. Upon observation, this energy collapses into a definite state, causing us to perceive the familiar material world, which is comprised of matter, atoms, particles, and ultimately, waves.